Hello class, this is day 15, period 4. I'm going to cover yesterday's homework, do a couple more questions from the text. We're going to look at the structural effects and what it does to the strength of an acid. And then I'll talk about the special case of sulfuric acid, which is a mixture of a strong acid and a weak acid. So how do you calculate the pH of an acid that has those peculiar properties? So the first thing we're going to look at is page 718 of the text, where it asks you to calculate the number of H plus ions in 1 milliliter of pure water at 25 degrees Celsius. Milliliter of H2O at 25 degrees Celsius, Kw is equal to 10 to the negative 14. So 1 milliliter, remember that molarity is equal to the number of moles divided by the volume. So is it asking the number of H plus ions? So let's find out the number of moles for starters. The molarity of H plus is going to be 10 to the negative 7 in neutral water, because the ion product, remember, is made up of the H plus concentration times OH minus concentration, and in neutral water equals 10 to the negative 14. So if you take the square root of 10 to the negative 14, you get 10 to the negative 7. The volume is 1/1000th of a liter. And so you get 10 to the negative 10 moles of H plus. Multiply that by Avogadro's number, and it gives you 6.02 times 10 to the 13. Okay, that's an easy question. That was one of the questions you had in the test, so most of you got it right. The next thing I wanted to look at was 116. The question asks this: the structural formula for acetic acid is shown in table 16.2. I'm going to draw it on the board in a minute. Replacing hydrogen atoms on the carbon with chlorine atoms causes an increase in acidity as follows. So acetic acid has a Ka value of 1.8 times 10 to the minus 5. If you add a chlorine atom, it has what's called an inductive effect. So if you were to look at the structure of acetic acid, it looks like this. So when it ionizes, you get that. So there's a negative charge on the oxygen. Now that negative charge can come down here, and this will flip up over there. So you get two possible resonance structures, they call them. Really what's going on is you're sharing 3 bonds over 2 positions. So the electron density here is a little higher because of that negative charge. Okay, so it's being distributed between those 2 oxygen atoms. So if you have something that has a highly electronegative atom in this position, it helps to draw some of that electron density down and away from the oxygens and helps stabilize the anion. So if you have chloroacetic acid, one of these hydrogens becomes, so instead of having 3 hydrogens, you'll have 2 hydrogens and a chlorine. This has a Ka equal to 1.8 times 10 to the negative 5. If you add a chlorine atom, all of a sudden the Ka increases to 1.4 times 10 to the minus 3. If you put 2 chlorine atoms, the Ka goes up to 3.3 times 10 to the minus 2. And then if you have a 3rd chlorine atom, it goes up to 0.2. So adding electron withdrawing groups to the carbon that is adjacent to the carbonyl will increase the strength of the acid because it has a stabilizing effect on the conjugate base. And then they ask you, using Lewis structures as the basis of your discussion, explain the observed trend in acidities in the series. Calculate the pH of a 0.1 molar solution of each acid. Trichloroacetic acid is used to help precipitate proteins in the lab setting. If you want to remove proteins from an aqueous solution, you can throw in a little trichloroacetic acid, and almost all the proteins will be protonated because of the high pH, and they will precipitate out of solution because they become less soluble in water. Let's just do. It says, using Lewis structures as the basis of your discussion, explain the observed trend. We just did that. Calculate the pH of a 0.01 molar solution of each acid. We're going to do an approximation calculation. I don't feel like doing the quadratic formula for each single one. We'll just set up the equation so you see what we're solving for. So we're just going to be changing the Ka values and finding out the pH that results. So given that it's going to be equal to x squared over the acetic acid concentration minus x, we're going to approximate it down to x squared over that. And for the most part, it won't make a big difference. Actually, for the last one, it will make a big difference because it's only a 0.1. No, we're going to have to use a quadratic formula. Otherwise, we're going to get strange results. 0.01. All right, so this is 0.01. So in the first case, you're going to have 1.8 times 10 to the negative 5 is equal to x squared times 0.01 minus x. 1.8 times 10 to the negative 5 times 0.01 minus x equals x squared. 1.8 times 10 to the negative 7 minus 1.8 times 10 to the negative 5x is equal to x squared. So the trinomial you get is x squared plus 1.8 times 10 to the negative 5x minus 1.8 times 10 to the negative 7 equals 0. And then we can enter that into our quadratic formula on the calculator to obtain the result. So the first number is 1, enter. The second number is 1.8 exponent negative 5, enter. And the last number is negative 1.8 exponent negative 7. And your value of x1 is 4.1535 times 10 to the negative 4. This one's going to be negative 4.333 times 10 to the negative 4. This is the correct answer. This one we discard. The pH from this solution will be the negative log of the H plus concentration that results, which is 4.1535 times 10 to the negative 4. So what you get for this one is mode normal log 4.1535 exponent negative 4, and you get a pH of 3.38. pH of 3.38 from the solution of the first acid. Now what if we use chloroacetic acid with a Ka of 1.4 times 10 to the minus 3? So now this will become 1.4 times 10 to the negative 3. So what you'll get is everything will be different from that point on. So let's write the pH that we get from each one. So 0.01 molar solution. And the pH that results, here it's 3.38. As we do each one, we'll write the result there and we'll erase the one that we've used. Okay? So that becomes 2 orders lower, 1.4 times 10 to the negative 5. minus 1.4 times 10 to the negative 3x equals x squared. Trinomial becomes x squared plus 1.4 times 10 to the negative 3 minus 1.4 times 10 to the negative 5 equals 0. Let's enter the values that result. 1 in the first case, 1.4 exponent negative 3 in the second case, minus 1.4 exponent negative 5 in the last case, and you get 3.1065 times 10 to the negative 3 and negative 4.5065 times 10 to the negative 3. That's the correct value. That one you discard. So negative log of 3.1065 times 10 to the negative 3 equals pH at 2.5. 2.51. So you get a pH of 2.51 if we use that acid. Okay, that one's taken care of. Next one is if we use dichloroacetic acid. With dichloro, the Ka value becomes 3.3 times 10 to the negative 3. This becomes also 3.3 times 10 to the negative 3, and everything after that changes. So we go 3.3 times 10 to the negative 5 minus 3.3 times 10 to the negative 3x equals x squared plus 3.3 times 10 to the negative 3x minus 3.3 times 10 to the negative 5 equals 0. There's your trinomial for entering into the you imagine if you're doing this by hand using the quadratic formula, it would be very time consuming. That's why it's good to learn how to use your calculator. Equation, quadratic, first number is 1, enter, second number is 3.3 exponent negative 3, enter, minus 3.3 exponent negative 5, enter, and you get the following numbers for x1 and x2. You get 4.3268 times 10 to the negative 3 and negative 7.6268 times 10 to the negative 3. This is the correct one. Use that. Negative log of 4.3268 times 10 to the negative 3 is going to give you the pH. So log of 4.3268 exponent negative 3 gives you pH at 2.36. So for Ka is 3.3 times 10 to the negative 3, you get a pH of 2.36. And finally, the last one with a Ka of 0.2. This changes to 0.2. And the rest is all different. So you get 0.2 times 0.01 equals 2.0 times 10 to the negative 3 minus 0.2x equals x squared. So x squared plus 0.2x minus 2.0 times 10 to the negative 3 equals 0. That's your trinomial for entry into your calculator. The mode, equation, quadratic. First number is 1. Second number is 0.2. Third number is negative 2 exponent negative 3. And what you get is 9.5445 times 10 to the negative 3 and negative 2.095 times 10 to the negative 1. So the pH, which equals negative log of H plus, and this equals your H plus under these conditions, is the log of that number. So put back the mode normal, log of 9.5445 exponent negative 3 gives you a pH of 2.02. So with a Ka of 0.2, your pH goes down to 2.02. So with the same concentration of acid, you see the different ranges of pH you can get. And if you take any protein and you reduce its pH to around 2, you're going to get protonation of a lot of the amino acid residues on the protein. It's going to cause the protein to become less soluble in water, and it'll precipitate. So that's a widely known biochemical trick, if you want to say. Okay, so that's number 116 done. And we discussed, so you can see the structural effects just by taking the same acid. So this is regular acetic acid, 1 chlorine, 2 chlorines, 3 chlorines. You see the same concentration produces lower and lower pHs. It's a stronger and stronger acid. Last one was 119. It says the volume of an adult's stomach ranges from about 50 milliliters when empty to 1 liter when full. If its volume is 400 milliliters and its contents have a pH of 2, how many moles of H plus does it contain? Assuming that all the H plus comes from HCl, how many grams of sodium hydrogen carbonate will totally neutralize the stomach acid? That's a good question. Let's work on that together. Of the board here. Little did my wife know that her home was going to turn into a classroom. So pH is equal to 2, volume equals 400 milliliters, and they're asking you moles of H plus. All right, so let's begin by finding out what the concentration of hydrogen ions is. If the pH is 2, it means the H plus concentration is equal to 10 to the negative 2. If you have a volume of 400 milliliters, then we can find out the moles. The number of moles is equal to the molarity times the volume. The molarity is 10 to the negative 2 moles per liter, if you want. And the volume is 4 1/100ths of a liter. 400 1,000ths of a liter, sorry. So the liters cancel, and you have 1 exponent negative 2 times 0.4. You'll notice I said 1 exponent negative 2. I said that because on the calculator, when I press the exponent button, it already enters the times 10 part. So I didn't make a mistake. That's actually entering the correct value. When you write 1 exp button negative 2, what it's saying in the calculator is 1 times 10 to the power of negative 2. Okay, be careful when you enter, because some kids do that. They press the exponent button, and then they say times 10 to the power of something, so they end up making 10 times order of mistake. So that's how many moles of H plus ions are present. And it's coming from HCl. So HCl has a molar mass of 1.00794. Oh, wait a second, is that what they're asking us? Might not be. How many moles of, assuming that all the H plus comes from HCl, how many grams of sodium hydrogen carbonate will totally neutralize the stomach acid? Okay, for that's not what they're asking us. But you know what? Let's do it anyway for fun. 35.4527 grams per mole. I just want to say how many grams of hydrochloric acid that equals. And then we'll find out how many grams of sodium hydrogen carbonate it takes to neutralize it. So hydrochloric acid, 35.4527 plus 1.00794, molar mass of 36.46 times 4 exponent negative 3 gives you a 0. Is that all? Huh. 0.1484256 grams of hydrochloric acid. Doesn't take much, does it? Mind you, the digestion in your stomach is probably carried out by enzymes more than the hydrochloric acid. The hydrochloric acid just establishes the correct physiological pH for the enzymes to achieve their maximal efficiency. It's not a disease, it's more like the effects of old age. As you get older, your stomach makes less hydrochloric acid, and you get something called achlorhydria. It just means absence of hydrochloric acid. So when you get not enough hydrochloric acid in your stomach, your digestive enzymes don't work as effectively, so it takes them longer to digest your food. So as you get older, you notice you go and eat foods that you used to eat when you were a kid, and they just sit there for like 3 hours. It feels like you have a brick in your stomach because you don't digest your food as well as when you were young. And it's probably related to the fact that there's not enough hydrochloric acid in your stomach. So they make enzymes you can take. You can take something called betaine hydrochloride, which will make up that difference that your own body is lacking, and then you'll find your food digests much more effectively. Anyhow, let's continue the calculation. You have, you're using sodium hydrogen carbonate, NaHCO3, to neutralize. So you have to neutralize that many moles of H+. So remember, there's one equivalent of neutralizing power with carbonate, because what happens is it protonates the hydrogen carbonate. So let me show you what happens. You get HCl reacting with the carbonate anion, sodium bicarbonate, and the result is you get H2CO3, which then breaks down into H2O and water. You get fizz and it releases gas. So that's how it neutralizes the acid in your stomach when you take sodium bicarbonate. That's what that is. Baking soda, the best antacid. So the number of moles, whatever moles of HCl you had, you're going to need the same number of moles of sodium bicarb. So let's find out. You're going to need 4.0 times 10 to the minus 3. So we're going to need 22.98977 plus 1.00794 plus 12.011 for the carbon plus 3 times 15.394 for the oxygen grams per mole for sodium bicarb. So let's find out the molar mass of sodium bicarb now. 22.98977 plus 1.00794 plus 12.011 plus 3 times 15.394. Molar mass is 84. Just write that over here. 84.00691 grams per mole. And you need 4.0 times 10 to the minus 3 moles. So to neutralize that much concentration of acid, you need 0.3360276 grams of sodium bicarb, and you're going to report your answer to 2 sig figs. Not even 1 sig fig because it's a pH of 2. So you can say basically 0.3 grams of sodium bicarb. That's your final answer, because they reported the pH is 2, no decimals. Okay, now let's just do one last thing, and that is when you deal with sulfuric acid. Sulfuric acid is a combination strong acid, weak acid. So the first protonation of sulfuric acid, the first deprotonation of sulfuric acid results in the formation of the bisulfate anion, and then the bisulfate anion can also donate a proton, giving sulfate, so that you, but it's a weak acid. The second ionization is a weak acid. So what if you get a dilute solution of sulfuric acid? How do you calculate the pH? Well, then you calculate it as the result of a mixture of a strong acid and a weak acid. So let's do that. So Ka sub 1 for sulfuric acid is essentially infinity, dissociates completely. Ka sub 2 is 1.2 times 10 to the negative 2. So when you have sulfuric acid, H2SO4, the first dissociation occurs completely to give you a proton and the bisulfate anion. But then you get another deprotonation where you get more protons and the sulfate anion. Okay? This is the one that's Ka sub 2 is 1.2 times 10 to the minus 2. So here's your question. What is the pH if 0.03 molar H2SO4 is present? Okay, so answer to that is assume the first dissociation occurs completely. So right off the bat, your initial concentration of H plus, you're going to set up a little ice table, and you'll show your dissociation of bisulfate. So it's going to be like this: bisulfate dissociating to form sulfate anion and some additional H plus. So already it's going to be 0.03 here, because all the sulfuric acid is going to dissociate to form the bisulfate. So this is going to start off at 0.03. That's your ice table. So initially it'll be 0.03, but then some of this will dissociate, so it's going to decrease the concentration of the bisulfate because it's going to turn into sulfate. So you're going to have 0.03 minus X at equilibrium. You don't really care what the sulfate concentration is. I'm not, well, okay, let's write it because it helps in our equilibrium. Initially it's going to be 0, and a certain amount X is going to appear, which is going to equal the amount of bisulfate that dissociated. So whatever amount of bisulfate dissociates, you're going to get that amount, the same amount of sulfate appearing. So at equilibrium it's going to be X. Your initial H plus concentration from the first dissociation is already 0.03. Extra protons are going to appear as this dissociates, because the protons from here are going to add to these ones. So at equilibrium, you're going to be 0.03 plus X. All right, so there's your ice table. This is where the ice table's power is really evident, because it helps you keep track of all different quantities. At equilibrium, Ka sub 2, which equals 1.2 times 10 to the negative 2, is going to equal to X times 0.03 plus X over 0.03 minus X. What does that represent? It represents the sulfate anion concentration times the H plus concentration total, because the H plus that was here plus the extra H plus. You may have to write total, you can just leave it like that. And the bisulfate anion is the initial thing. Okay, so that's what that's representing. So you're definitely going to use the quadratic formula to solve this. So you're going to get 1.2 times 10 to the negative 2 times 0.03 minus X is equal to X times 0.03 plus X. So we're going to simplify all that to write a trinomial. So 3.6 times 10 to the negative 4 minus 1.2 times 10 to the negative 2x is equal to 0.03x plus x squared. That simplifies to x squared. So 0.03 plus 1.2 exponent negative 2 gives you 4.2 times 10 to the negative 2. And this gets just transposed, so it becomes negative 3.6 times 10 to the negative 4. So now let's solve for x. We'll go into the quadratic mode equation. First number is 1, enter. Second number is 4.2 exponent negative 2, enter. And the third number is negative 3.6 exponent negative 4. And when you enter all that, you get your x value is 7.30194 times 10 to the negative 3 and negative 4.93019 times 10 to the negative 2. So the H plus concentration is based on this, not that. Why am I hearing music? Oh, that's why. Okay, so the pH is going to be negative log of that number. So log of 7.30194 exponent negative 3 gives you a pH of 2.13656, and that rounds down to 2.14. So the pH of your sulfuric acid solution, your dilute sulfuric acid solution, is going to be 2.14. Notice that the second dissociation had a notable effect on pH. If it had just been based on the first dissociation, you would have had 0.03, but there's a significant amount of acid that, if it had been 0.03, let's see what the pH would have been just with the first dissociation. So log of 0.03 gives you 1.52. Wait a second. 0.03. Log of 0.03. Something's wrong. Okay, I'm going to check the calculation and I'll let you know in the comments if I made a mistake. The setup is essentially right. I just may have overlooked something. Okay? Try this. Using the same technique, calculate the pH of question. Calculate the pH of a 0.075 molar H2SO4. Okay? And we'll talk tomorrow.